Thank you everybody for inviting me to speak today at this conference. I'm Susie Speller from the University of Oxford in the UK, and I'll tell you a little bit today about the work that we've been doing in Oxford on processing and testing of MGB2 bulks. In particular, we've been looking at how we can process them to tailor the microstructure to improve JC in these bulk samples. So the people that have been involved in the work are shown, some of them are shown here. So Guillaume Matthews was one of my PhD students who completed a few months ago, and Zilin Gao is another PhD student who's in the late stages of her project, and Chris Grosvenor has co-supervised those two with me. There are also some other people who have contributed to the work, which I will show at the end. The reason that we've been working on this project is particularly to make bulk magnets for applications where MGB2 might give improvements over permanent magnets. So one of those kinds of applications is shown here. This is a magnetic drug targeting experiment where what you might want to do is to have inject into the bloodstream some drug in little bubbles tagged with magnetic markers, and then use a magnet externally on the body to trap them at the location where you want to release the drug, so that you can make the drug more effective at the location you want it to be. And at the moment, permanent magnets are used in the experimental sort of demonstrators of this technology, but really they're not strong enough. They can't produce strong enough forces to be able to trap magnetic particles either too far into the body in blood vessels that are inside the body, or with blood flow moving very fast. And so increasing this magnetic force by maybe using a superconducting bulk magnet is one way we could think of improving the technology. Another might be compact MRI machines, for example, for doctors' surgeries and things like that, where again increasing the magnetic field a little bit from the permanent magnets might be useful. Okay, so why MGB2? So bulk superconductors are great because they can produce magnetic fields in rather compact geometries, but a lot of people will talk about using Rebco bulk materials. But MGB2 is much cheaper. We can make it polycrystalline. In fact, we want to make it polycrystalline because grain boundaries are good pinning centers in MGB2. And because we don't need to grow it as a single grain, we can process it by scalable techniques. Ones where we can imagine making bigger samples or mass processing the bulks much more easily. And it's got a relatively high transition temperature, of course, nothing like Rebco, but still useful enough that 20 Kelvin or even a little bit higher might be possible. And in particular, in our study, we're interested in operating somewhere near a 27 Kelvin, because if we want to make compact magnet systems, it might be useful to use liquid neon as the cryogen, which has a boiling point of 27 Kelvin. So there's a reason why we're particularly interested in that temperature. And up till now, a lot of the work on MGB2 has been to optimize its performance either at 4 Kelvin or at 20 Kelvin. So we've been looking at trying to optimize at slightly higher temperatures. So the main method that's used to improve JC in these bulk materials is to carbon dope. So carbon doping does several things. One of them is substitute for boron to increase the upper critical field of the superconductor. You can also get sort of artificial pinning centers introduced if you use the right kinds of dopants and do the right kind of processes. So here's just an example on the left of how adding some sort of carbon-based materials can improve the properties. Compared to the blue line, you can increase it using silicon carbide, or in this case, malic acid. And that's great. You improve the upper critical field, so it drops off, the field drops off at a much higher value along the x-axis there. But the problem with it is that when you introduce carbon, you also drop TC. And that's okay if you're operating at 20 Kelvin, so long as you don't go too far. But if you want to operate at 27 Kelvin, we don't have much headroom available for letting the critical temperature drop. So the sort of motivation of our study was to try to look at different ways of improving JC, but without introducing this reduction in TC. The way we've gone about doing it is to use not the in situ technique, which is often used, where you add Mg and boron powder separately, mix them up, and then do a reaction. Instead, we've been looking at the ex situ route, where you start with Mgb2 powder, and then you do a consolidation process. And the method that we've used mainly for our study is called field-assisted sintering, which is equivalent to SPS. And so it's a very fast technique. About 5 minutes we have it at temperature, and it exerts a little bit of pressure, about 15 megapascals. And for MgB2, if you want to do fast processing, you need both relatively high temperatures and pressures, at least more than atmospheric pressure. And our general sort of test samples are about 20 millimeters across, although we can make bigger ones than that. To start off looking at what we actually make with this ex situ process, we're just going to look at what happens when you change the temperature of the processing and what happens to the microstructure of the samples. So as you increase the temperature from 900, that's the top left, to 1200 degrees C, that's the bottom right, what you should be able to see quite clearly is that it gets much denser. So in the top left picture, we've got sort of isolated agglomerated powder particles with gaps in between. And in the bottom right picture, it's pretty much fully dense. Not completely, but nearly fully dense. The dark grey phases you see in there are MgB4, which is a decomposition product from MgB2. You can also see some bright white particles in there, and they are MgO, which also forms during the process, and there'll be some of it already in the starting powder. The other thing that happens, although it's not obvious from these particular microstructures at these magnifications, is that the grains coarsen as we increase the temperature, as you would expect. So you can probably see that most clearly with the difference in MgB4 that you can see as the temperature increases. But we've done lots of analysis to show that that's what's happening. So really, if we want to use the field-assisted sintering technique, we need to go to temperatures of 11 or 1200 degrees C in order to get fully dense bulks. If we look at the effect on the properties of that sintering temperature, what we've done here is magnetization measurements on small samples that are a couple of millimeters in dimension, and the critical current density has been extracted using Bean's model. I'm going to come back to that in a minute. But what you see is it looks, as you increase the temperature, you go upwards by that green arrow, and it looks as if the performance, particularly at low field, the JC is increasing. It's a log scale, so it's six-fold probably at 0. It's a little bit more actually at 1 Tesla. But you can see that the field where the critical current drops off, which is the sort of zero resistivity field, doesn't really change very much with temperature, so it all drops off at around 4 Tesla. But what I want to do before I carry on about the sort of processing is to just explain a little bit about the magnetization measurements and interpretation of those magnetization measurements. So we have some microstructures that are not fully dense in our samples. You saw that the low temperature sample had these sort of agglomerated powder particles that didn't look to be particularly well connected. So the cartoon on the left is a sort of picture of what that sort of looks like. Whereas at higher temperatures, we had something more like what we see on the right there, a sort of fully dense material. And in terms of what happens when you do a magnetization measurement, you induce current loops inside the sample. And if you've got a fully connected sample, the current loops go all the way around the outside and all the way through in concentric sort of loops all the way to the middle. And Bean's model extracts the JC value, assuming that's what the currents are doing. So if you look underneath the right-hand picture, there's a formula there saying delta M connected, that's the fully connected value, is equal to dJC times G. Now, the D is the sample diameter, roughly. JC is the current density that's whizzing around through the sample, which we assume in Bean's model to be the same everywhere. And G is just some geometry factor, depending on the sample geometry. And so what we do in the measurement is we measure delta M, which is the width of the hysteresis loop, and we extract JC from it, knowing the sample geometry and the dimensions and things like that. But if we look at the situation on the left-hand side, which is much more like we have in the real microstructures at low temperature, then you need to modify your formula because your loops are going around within small particles rather than through the whole sample. And so you have a slightly modified equation where you've got the sample, the sort of particle size, small lowercase d, you've got some volume fraction in there, and then you've got the JC and the geometry factor. And in our particular samples, the sort of particle size is, I don't know, something like 10 to 100 microns. It depends on what we do. And the actual sample size that we use to test do these magnetization measurements is about 2 millimeters. So even if it was fully dense but unconnected, so even if the volume fraction was 1 but the sample was unconnected loops, then we would expect the hysteresis loop, the width of the hysteresis loop, to be 20 to 200 times different. So the one on the left will be about between 20 and 200 times smaller than the one on the right. And if we just use Bean's model with the sample geometry to extract JC, it's going to look like a much lower JC than it is actually flowing within those particles. So we've got to be a bit careful about how we interpret the JC data. It doesn't necessarily mean that the intrinsic JC of the material is poor just because we see a smaller magnetization loop or a smaller JC extracted by Bean's model. So if we look back at that microstructure, in probability we've got something between the two in a real sample. We've got some microscopic current loops, but we've also got some macroscopic current loop, and the magnetization will be a sum of the two. And that makes it rather difficult for us because we can't then extract either the macroscopic or the microscopic JC with much confidence from the width of the magnetization loop. Although if you look at the formulae, because the microscopic currents, if you've got relatively small particles, are orders of magnitude smaller than the macroscopic currents, you actually need to have very poor connectivity before your magnetization loop has much contribution from the microscopic loops in there. So in general, it's the macroscopic current that you'll be measuring if there is any at all. Okay. But one of the things that may be not so obvious is that the connectivity, so how well the sort of macroscopic current can get through the sample, might be dependent on field. So we can come back if you want to why that might be. But it may not just be geometric, therefore it might change with field. And the consequence of that is that if you want to do something like pinning force analysis, where you're looking at fitting the JC or the pinning force, which is extracted from JC, as a function of magnetic field, it may not be possible in the same way that you would normally do it, because there might be some field dependence that isn't just the field dependence of JC. So it makes it quite difficult to extract what kind of mechanisms are operating. There are also other problems with you doing pinning force analysis on this kind of material. In particular, the anisotropy of MgB2 means that there will be some sort of percolation effects that contribute to the JCB performance, even the intrinsic JCB performance, without having to consider this connectivity issue. So I thought I'd just mention that before we carried on to explain why it's not always straightforward to do to look at the mechanism by which you're changing your pinning when you do different things to the processing. So coming back to the strategies that we've been using to try to enhance JC, particularly at higher temperatures, one of the methods we've been using is something that's used in the steel industry called oxide dispersion strengthening. And the idea here is that you take something insoluble in the host material and you make it dissolve by using a high-energy ball milling process. And an example of what we can do in MgB2 is add something like yttria, Y2O3, which ought to be insoluble in the matrix, but we can force it to dissolve. And then, if you do the consolidation, the heat treatment associated with the consolidation process, you will precipitate out some particles because it doesn't want to be there dissolved in the matrix. So you can generate a nanoscale distribution of these insoluble impurities that have been dissolved under non-equilibrium situation. So we want to try to replicate this in MGB2. This is it in steel. We want to try to replicate it in MGB2 because a nanoscale dispersion of particles is exactly what we want to improve flux pinning. So here's the process. We take the MGB2 powder and we add yttria powder, and we do the high-energy ball milling, and then we use the field-assisted sintering technology to do the consolidation process. So if we first of all look at the ball milling situation, what happens there, here are some TEM images and EDX maps of individual particles after different milling times. So the first one's 10 minutes, so it's hardly been milled at all. And then we've got 1 hour and 12 hours milling. And hopefully what you can see from the colours in there is that as we go on with the milling process, the yttria and the oxygen distribute throughout the powder particle. And so it looks as if we're dissolving it. We can't prove we've actually dissolved it rather than broken it down into very, very tiny particles, but it's essentially dissolving in the matrix on a very fine scale. And after that, we can also look at the XRD to show that something's happening. This is just a couple of the peaks. The right-hand one is the MGB2 peak, and what you see when you're ball milling is that the height of that peak comes down, and also the yttria peak disappears. So the height and the width, the broadening of the MGB2 peak is because we're dissolving the yttria in it, and we're putting in lots of disorder during the ball milling process as well. So that's sort of just confirming that we're dissolving this yttria. And then we do the consolidation process using the fast machine. Various things, different weight percents have been tried in different milling times and different temperatures and things like that. But I'm going to show samples that have been consolidated at 1150, so it's should be rough, pretty much fully dense. So what does the microstructure of the bulks that we make look like? These are some TEM STEM EDX maps again, showing the final microstructure. And you can see that the little green particles that we get are actually yttria YB4. So it doesn't reprecipitate as yttria that we put in. It precipitates as YB4, and you also get some MgO formed, both on the scale that are good for flux pinning. The YB4 is particularly nice, sort of tens of nanometer size particles, which are ideal. So what happens to the superconducting properties when we do it? Well, so here we're seeing the blue is the pure MGB2 without any yttria, and then we have yttria 0.5 weight percent added, milled for an hour, milled for 12 hours, and then the purple line is a bit more yttria added 2 weight percent. And you can see that you get a little bit of a drop in TC, but not very much. So a couple of degrees, and that's all. And at 0.5 weight percent, it's maybe about a degree, which we could just about cope with, I think, for our application. If we look at the critical current density, now I've called it apparent JC, just based on the argument that we had before, that if it's not fully connected, then it's not necessarily the actual critical current density in the material, but it gives us an idea. It probably gives us an idea of the macroscopic current density here. And what you can see is if we compare the blue line, which is completely underneath the orange line, and then compare it to the ones that have been milled for longer and processed, you can see that we increase JC and also push the upper critical field out, or the irreversibility field out to the right. So we've made improvements by adding this yttria. If we change the sintering temperature, so this is 950 in the blue line, going up to 1150 for the green line, you see that if we do it at too low a temperature, we don't recover the damage that we put in during the ball milling process fully. And so there will still be some yttria dissolved, and we still have some disorder from the strain that's reducing TC. And again, we can look at the JC performance. And what you can see is that as we increase the temperature, we're improving very much the current density down at low temperatures, the apparent current density at low temperatures. And we're also, the main problem is that we're also reducing our sort of irreversibility field, or the field at which the resistance goes to zero in this material. And ideally, so this drop in JC at low fields is the connectivity issue that I was discussing before. So the green sample, the higher temperature process sample, is just better connected, so it looks like it's got a higher critical current density. But obviously, as we recover the disorder that we've put in to the material, our upper critical field is being affected. It's being reduced again back to somewhere nearer the pure MgB2. So what we'd really like to do is to come up with a process that would not only increase the low field JC, so make sure that we've got fully dense, well-connected microstructures like we do at high temperature here, but also pushes keeps the performance at high field as well. So there's this is just what I've just said, the interpretation of those data, that information. So at low processing temperature, TC is not fully recovered because of the disorder. The high field properties are improved. More the increased HC2 and the improved flux pinning. We've got a finer microstructure. The load field properties are apparently poor, and that's because of the poor connectivity. If we go to higher sintering temperatures, TC is only slightly suppressed, but we've got better connectivity, which leads to better fields, better performance at low fields, but the high field performance isn't so good. So we want to develop these strategies that will allow us to optimize over the whole field range. So the first approach we've taken is to look at ultra-high pressure synthesis. And we've done this at Element 6, which is a company which has got a research lab in the UK, and they make synthetic diamond in their presses. So they've got these big industrial presses. So we've looked at using 5 gigapascals pressure rather than 50 megapascals that we use in the fast. And you can see now that the advantage of that, if you compare the microstructures on the left, is that at the same temperature, at 900 degrees C, we can pretty much fully densify the material at 5 gigapascals, whereas in the fast process, we couldn't. It was almost isolated particles. So what does that do to the performance? If you look at the purple line, that's the 900 degree ultra-high pressure processed sample. And you can see that maybe at low fields it's not quite as good as the fast sample, but it's better at high fields. So we've got much better performance at high fields. So that was the first approach, and that's looking promising. The second approach is to look at whether we can do some liquid phase sintering to try to get the connectivity better without having to increase the sintering temperature. And magnesium melts at around 650 degrees C, so lower than the processing temperature we've been using. So we've been looking at whether we can use it as a sintering aid in MgB2. So here's some XRD showing what happens. We've added 2 different amounts of magnesium here, 3 weight % in orange and 10 weight % in green. And what you see is that actually the 3 weight % magnesium, you actually get an increase in the MgB2 peak intensity, which is interesting, but you also see a decrease in the MgB4, that's the star. You see it at just under 36 degrees there. So that peak disappears, and the more magnesium we add, the lower that peak gets and eventually disappears. What's happening is that our additional magnesium is reacting with the extra magnesium, is reacting with MgB4 and producing more MgB2. So it's stopping the decomposition reaction and in fact reversing it because we end up with less than we started with by adding this extra magnesium. If we add 10 weight %, we actually get some excess magnesium in the microstructure as well. You can see that by the green curve with the cross, the peaks with the crosses above them show that we've got some excess residual magnesium left over that hasn't reacted. So microstructures, so the top one again is our 900 degrees C with no magnesium added, and the bottom one is when we've added the 10 weight % magnesium. So hopefully you can see that the microstructure looks much better connected there. We've done some transport measurements in the normal state to work out the connectivity, And you can see that as you increase the magnesium, the blue line, the connectivity percent, increases just as the microstructure suggests it is. So it goes up quite a lot actually, from about 5%, which is very low, up to about 25%. So that's interesting, and it matches the images that we've got here, the microstructures.
I'm sorry, Susie, you have 2 minutes left.
Yeah, we're nearly there. Yeah. So just looking in more detail at where this excess magnesium is, because there would be a worry that the magnesium might form magnesium oxide at the boundaries, or magnesium layer coating the boundaries, which would stop the current getting through. Actually, we've done some STEM EDX and looked very carefully, and can't find it other than in these little pockets at the grain triple points of the grain boundaries. So again, that's promising. Looking at the superconducting properties, addition of magnesium doesn't do anything to the critical temperature. It keeps it nicely the same. And here, if we look at the JC, we're enhancing JC over the entire range of magnetic field by adding up to 6 weight percent. So if we add 10 weight percent, it gets worse again at high field. But if we add up to 6 weight percent, then we're improving JC quite a lot over the entire field range. Okay. So just to summarise, when you've got inhomogeneous samples like these MGB2 bulks, you've got to be careful about interpreting the magnetisation results because the microstructure makes a big difference to the current distribution, and you have to take that into account when you're doing the interpretation of the results. The nanoscale artificial pinning from adding yttria works quite well in combination with FAST. The challenge is to increase the connectivity of the samples without coarsening the microstructure. Ultra-high pressure synthesis is one way we can do it, but another way we found is to use this liquid phase sintering technique to add some magnesium to the starting powder. So thank you. I will just put up the acknowledgements. Thank you. Are there any questions?
So are there any questions? Please.
Thank you for your presentation. Did you experience any magnesium loss during your process? And did you have any? Did you make any measurements for different magnesium content at the surface of the sample and at the inner sides of the sample?
So the FAST process puts on some pressure, so it's at 50 megapascals, which does help to reduce the magnesium loss. I don't think, I'm not entirely sure, because of course it was my students that did this. I don't think we looked for any magnesium at the surface, but for sure we get some excess magnesium left in the bulk if we don't, if we add too much.
Thank you very much for an interesting talk. I have a question because I understand that your motivation is to use these bulks at 27K, but you showed critical results only for 4K, for helium temperature. And my question is whether you believe that the effects on the performance will be the same at higher temperatures, because I'm afraid it could change.
Yeah, you're right, and we have measured at 20 and 27 Kelvin as well. So the full data sets are there. And you're quite right that I've shown the 4 Kelvin data because the changes are most dramatic there. So all the changes at higher temperature, they mimic the same thing actually, but they're just less dramatic. So the improvements are less dramatic. So we have all the data. I just showed the 4 Kelvin data because it illustrated the points most clearly and visually for the talk. So yes, you can. We have some publications on the yttria ODS material already, and the magnesium doped. We've submitted the paper for that, so hopefully you'll be able to look at all the full data sets very soon for that.
Okay, thank you very much.
Are there any questions? So Susie, you may look at your chatting area. There are some questions over there. For example, Sherer Hossein asking some question.
Okay, let me just look. So, okay. How did you apply the huge 5 gigapascal pressure? Is that during the sintering? Yes, so the 5 gigapascal pressure was done at element 6 using their industrial cubic presses. So you press from all directions whilst you're heating. So that's the process that we use. We have made larger samples with them. The problem with the very ultra high pressure technique is that the samples crack if you're not careful. So we had some successes, but it's often the case that you get cracking in there. So what we haven't done yet, and what element 6 are absolutely sure we can work out, is the way to take off the pressure in such a way that we don't crack them during the cooling down process and the removal of the pressure. So that's the big difficulty with the ultra high pressure. It may seem like a very extreme technique, but actually because it's industrially used, it would be something that could be used and could be scaled. Kevin asked...
You also answered that, and you may look at Yamamoto-san maybe.
Yeah, okay. So Yttria, did they form during ball milling or sintering? Okay, so yes, they form during sintering. So during ball milling, you just dissolve the Yttria, the Y203, into the MgB2. And when you do the consolidation, because it's metastable, you precipitate out the stable phase, which is YB4.
Okay, thank you.